All right, I want to walk you through some of the basics of hang time. First off, look at this problem here. Little mouse jumps up into the air after being startled, and we have a velocity versus time graph that's given to us. And the prompt says, using the velocity versus time graph shown at right, describe the mouse's direction of motion for its entire motion using parts of the graph vocabulary. And so what we have here is just a little way to organize your response. On the left-hand side, this is the parts of the graph. And then the right-hand side is the physics concept, or the motion itself. What does it mean? If you need to review these for position and velocity graphs, this one is a velocity graph. At the beginning of your packet, I think it's probably page 3, there's a good review that goes through each part of the graph and what it means. Now, the way this works is we have the given, and then we have the this means. So given something about the graph, this means something about the motion. And you can see here, it says given that the y-intercept is in the, well, let's look, oh, it's in the positive quadrant, so let's circle that. It's in the positive quadrant. And then there's a little arrow here, so this is where it's going to finish or continue the sentence. Given that the y-intercept is in the positive quadrant, this means that the mouse has a positive initial velocity and is initially moving upwards in the positive direction. Given that the line crosses the x-axis, so this one's a little trickier. One thing to interpret velocity graphs, I always suggest, is to make up some numbers. So, for instance, this would be 0. This would be plus 10, this would be plus 5, negative 5, negative 10. And then we're going to plot some points. So it's like, oh, this is plus 8, plus 6, plus 4, plus 2, 0. Oh, those numbers are getting smaller and they're all positive. Now over here we have minus 2, minus 4, minus 6. Those numbers are getting bigger and they're negative. So the fact that it crossed the time axis means it went from positives to negatives. So what does that mean in terms of velocity? That's the direction. So that means it changed direction. So we can write this means the direction changed, or it changed, the mouse changed direction. And then the last one, given that the line ends in the negative quadrant, this means the mouse has a negative final velocity, is moving in the downwards direction. So that's just a review of velocity time graphs. With hang time, with free fall, nothing's different about those graphs. They're still just velocity time graphs. Now let's do the math. This is a bit trickier. How long would the mouse be in the air for if it could jump 0.025 meters high? Ignore air resistance. Okay, we're going to get to what this means in a second. I want to look over here first. This is the key to solving all of these problems. And so you want to fill out everything you know. All right, at point A, we don't know the velocity. Put a question mark there, leave it blank. It is not 0 because the mouse has to be moving in order to start jumping up in the air. To leave the ground, you're already moving. The acceleration is negative 9.8 meters per second squared. The position at A is 0, and the time is 0. At the apex, at the maximum height at B, the velocity, this velocity is 0. Acceleration is still negative 9.8 meters per second squared. The position, they did tell us, 0.25 meters high. So at this point here, that's how high the mouse is up in the air. We don't know the time. This would be the time to go from A to B, and we don't know what that is. And then the moment before hitting the ground, well, the height is 0 again. Acceleration is still negative 9.8 meters per second squared. The velocity, we don't know. It's not 0. Think about if you put your hand down and a bowling ball dropped on it. Why does it hurt? Because it is moving when it hits your hand. Just because it hit your hand doesn't mean it's not moving. And the time, we don't know the time. This is going to be, oh, we'll get to that in a second. So earlier in class or in the last video, we looked at choosing some start and end points. And the hint here is that we should choose B to C to begin with. B is always a good point to have involved because we know the velocity at B, and it's going to be 0. And we want to know how long, so this is going to be the time. So if I'm going from B to C, I'm going to start with B. Those are going to be my initial values. This is going to be my final values. And it looks like I want to solve for this time here. So I'll solve for the time from B to C. Now, that will not be my answer because I want to know how long the mouse is in the air. So I'm going to solve for this time here, and then I got to double it because I got to go up and down. Now I need to choose an equation. If I look at my two equations, I can't use this, not constant velocity. I have these two. I do not know the ending velocity, so I can't use this equation. So I'm going to use this. Make sure you copy it correctly and carefully because you don't want that to be the thing that is holding you up. All right, and now we just need to plug in some values. So x is the final position. That's the position at C, so that's 0. 1/2 the acceleration in free falls, negative 9.8 meters per second squared. The time is what I'm solving for. The next one here, you don't have to write this down, but it's the initial velocity, the velocity at B, which is 0, times t. Well, 0 times anything is 0, so that just kind of goes away. Plus the starting position, and the height at B is 0.25 meters. Then we just need to solve it algebraically. Do that real fast here. And let's see, so I get negative 0.25 equals negative 4.9 times t squared. Got to divide both sides by 4.9, or negative 4.9. Negative 4.9. And then, let's see, what am I going to get here? I'm just going to need to take the square root of whatever that is. Whatever 0.25 over 4.9 is. 0.25 divided by 4.9, 0.05. So then, if I come up here, you're going to get t squared is equal to 0.05. So t, I got to take the square root of that. I get 0.23 or 0.22. Not a huge deal if you round or don't round. So this is not my final answer. This is the time from B to C. It's from here to there. So to get the total time, I got to double it. So this is B to C. So T total, that is 0.44 seconds. And that would be my final answer for this. Okay, next one. With what velocity does the mouse hit the ground? So that means I'm looking for this velocity here. I'm going to go from B to C because I kind of know everything about all these things now. And notice the time I will use will be this one because that is the time from B to C. If my initial is at B and my final is at C, I got to use the time it takes to go from B to C. We got to choose an equation. Well, I want the velocity at C, and C is my ending point. So that would be my final velocity. So the only equation I can use is going to be this one here. The first one I can't use because it's only for constant velocity, and this velocity is changing. And the last one I can't use because it doesn't have final velocity in it. So I want to solve for final velocity. Acceleration is negative 9.8 meters per second squared. The time, now this is the time from B to C, the time to fall from the very top is going to be 0.22 seconds. Plus the initial velocity is 0 because that's the velocity at B. So that one's a little bit easier to solve. And I'm going to get a negative we'll round it, negative 2.2. And it's negative because it's moving down. Negative 2.2 meters per second. And And that should make sense because at C, it's moving down. So the key to solving these problems is not just plugging in a bunch of numbers. It's understanding what's being asked and what's being given. It's drawing a picture and adding information to that picture. And then it's choosing where to start. Honestly, B to C will be very common because this is the point where we know the velocity is 0. All right, there you go.